Okay, let's finally take a look at the chain rule. I say finally because in my last few videos I have referenced it a little bit because it's already popped up a few times, we just haven't recognized it. So before I go into the actual definition of the chain rule mathematically, I want to look at an example from a couple of videos ago, which was finding the derivative, finding d by dx of sine 2x. So in the video about differentiating sine and cos, I showed that this is equal to 2 cos 2x, okay? And I mentioned why. I mentioned that we know that sine differentiates to cos, and we also know that we've got a 2x inside here, and I said that we want to take this 2 and bring it outside. But specifically, I said that we want to take the derivative of this inside function and bring it outside. And then I said that this was the chain rule, and I said, trust me, and we'll get onto it. The chain rule applies when we have a function within another function. So two functions kind of smooched together. So here, I've got two different functions. I've got 2x as a function, and I've got sine as a function. Sine of x isn't two functions because it's just sine of x. There's no special function happening to x. So I've got sine of 2x, meaning I've got two functions. And the way we formally write this in the chain rule is we say we have y is equal to sine of u. So we have one function defined and then the other function is just replaced with u. So in this case, we have u is 2x. And the chain rule tells us that in order to differentiate this, we need to take two derivatives and multiply them together. One is the derivative dy by du, which is, of course, just cos u. Sine differentiates into cos. And then we need to take the derivative du by dx. We have u equals 2x, so the derivative of u with respect to x is just 2. And multiplying these together, we get 2 cos u, and putting back in my substitution, u is equal to 2x, and we get 2 cos of 2x, which is the same thing that we did the other day. Now, I also alluded to this in my last video when we were talking about exponentials, and I said e to the 2x, if I take the derivative of that, it is 2e to the 2x. And I can't actually remember if I said just take this number 2, bring it down in front, or if I actually told you to differentiate this thing here. Why? Because it is a function, which is 2x, which is my u, within another function. Y equals e to the u, e being the other function. And it's easy to see where these other functions are. So I've got these two functions. I want to find du dx, which is just 2, and I want to find dy du. Well, e doesn't change when you differentiate it, so I'm just left with e to the u, which is e to the 2x, u being 2x. Put those together, and I get 2e to the 2x, which we already know is the derivative of e to the anything x. So we can extend this to absolutely any function we want. Couple of key examples. So we've already seen a trig one, or a basic trig one, and a basic e one that we've seen before, but it applies no matter how complicated it is. E to the x squared plus 2. If I wanted to differentiate this, well, I'm going to do the same thing. I've got a function e and another function x squared plus 2 within it. Only ever two functions, by the way. If it's more than 2, it gets a bit trickier. We'll see that probably in the next video. But I've got a function u, which is 2x, which is x squared plus 2. And I've got my function y equals e to the u. Differentiate u with respect to x will give me 2x plus nothing, just 2x. And differentiating this, dy du, or de, that will just give us e to the u, because obviously e doesn't change. Throw these together, we get 2x times e to the u, which is 2x e to the x squared plus 2. Very similar looking thing to the last one. And what is one thing that's just key is we never want a u in the final answer, right? Whenever we do a substitution, we always want to put it back into x whenever we can, which is right at the end, which is why we need to rewrite this like that. So no matter how complicated it is, if we have a function within a function, then it is differentiable using I-chain rule. 2x squared plus 4 all to the power of 3 over 2. Well, this looks a bit annoying, right? You might think, oh, well, I can't expand it out, or maybe you can using some binomial expansion, but we're not concerned with that now. But what we can notice is I've got one function, u, inside another function. Let's say y. Y is equal to u to the power of 3 over 2. And u is 2x squared plus 4. So du dx, just the same thing over and over again. That's just 4x. dy du, well, u to the 3 over 2, that's just a normal polynomial. So I'm going to bring my 3 over 2 down, multiply it by the u, minus 1 from the power. So I get half. Put all of this together, I get 4x times 3 over 2, and then u to the half. And u is just 2x squared plus 4 to the half, or square root of all of that. This kind of thing will start to become second nature very, very quickly. As soon as you get good at recognizing when to use the chain rule, which, quick hint, is most of the time, if we ever have a sine, a cos, a tan, or an e, or a log, or most commonly, some really long, horrible thing to the power of something. Maybe it's a square root instead of a power of 3 over 2. Well, it's the same thing. That square root just becomes a power of a half, and we do the same process with the chain rule. In fact, after a while, you probably get so comfortable with this, you don't even need to write out your u's and your y's at all. You'll just be able to recognize that I've got an interior that I need to differentiate and take outside, differentiate the rest as usual, and we are good to go.